In the previous lecture, we saw some numerical differentiation techniques, namely via Taylor expansion and the method of undetermined coefficients. We shall learn some more methods by means of which numerical differentiation formulas can be derived. So, we know from interpolation by polynomials, we can approximate a function f of x in an interval or when its values are given at a set of points by means of interpolation polynomials. So, let us make use of this idea and then see whether we can get numerical differentiation methods from interpolation polynomials. So, we shall now discuss numerical differentiation by polynomial interpolation. By polynomial interpolation. So, we know that Pn of x is sigma k equal to 0 to n Lk of x into f of xk is the Lagrange interpolation polynomial that approximates the function f, where xk are points x0, x1, x2, etc. up to n. So, from the interpolation polynomial, Lagrange interpolation polynomial that approximates the function, one can obtain an approximation for the derivative f dashed, and it is defined by the derivative of the interpolation polynomial, and that is defined by sigma k equal to 0 to n Lk dashed of x into f of xk, and this polynomial Pn dashed of x is of degree at most n minus 1. So, here Pn of x is the interpolating polynomial that interpolates the function at a set of n plus 1 points, and Pn of x is of degree n. So, Pn dashed is a polynomial of degree at most n minus 1 that approximates the function f dashed, which is derivative of f. And this Pn dashed, therefore, when you look at this expression, is a linear combination of these polynomials which are obtained taking the derivative of Lk of x. So, this expression is a linear combination of the derivatives of Lk of x with coefficients given by the values of the function f at these points. So, the question now is, what is going to be the error in such an approximation? What is the error? We already have an expression for the error in interpolation, namely f of x minus Pn of x is given by pi n plus 1 of x into n plus 1th derivative at some point psi by n plus 1 factorial, where psi lies between x0 and xn when f satisfies certain conditions. We already have obtained the expression for error in interpolation, where pi n plus 1 of x is x minus x0, x minus x1, etc. up to x minus xn. So, let us compute the derivative and see whether we are able to give an expression for the error f dashed of x minus p n dashed of x. So, if I compute f dashed of x minus p n dashed of x from the above expression, then I get pi n plus 1 dashed of x into n plus 1th derivative at psi. Recall that psi is a function of x, it depends on x, by n plus 1 factorial, then plus I have pi n plus 1 of x by n plus 1 factorial into d by dx of the n plus 1th derivative of f as a function of psi of x. So, if I look at this expression, I observe that I cannot estimate the second term because I do not know the dependence of psi on x, and therefore, I cannot use this to obtain an estimate for the error in f dashed of x minus p n dashed of x. So, we must have some methods by means of which we should be able to estimate this error, and we have an alternate approach, and that is given by the following result in the form of a theorem. So, let us look into the results of this theorem. It says let n be greater than or equal to 1 and let f be a real valued function, defined and continuous, on the interval a b such that its n plus 1th derivative is continuous on the closed interval a b. And suppose further that xi for I is equal to 0, 1, 2, 3 etc. up to n are distinct points in the interval a b, and that p n is the Lagrange interpolation polynomial, of degree at most n for f defined by these points. Namely, the function f is reconstructed by seeking a polynomial p n of the Lagrange interpolation type that interpolates the function at a set of these n plus 1 points. So, it is a polynomial of degree at most n. Then the theorem says there exists distinct points eta I for I is equal to 1, 2, 3 up to n. There are n points where in the open interval a b, and corresponding to each x in the interval a b, there exists a psi which depends on x in the open interval a b such that the difference in f x and p n is given by the n plus 1th derivative at psi by n factorial into pi n star of x, where pi n star of x is x minus eta 1 into x minus eta 2 etc. up to x minus eta n. So, what does it say? f satisfies certain conditions. In addition, if you have distinct points xi in the interval ab and Pn is the Lagrange interpolation function polynomial for the function f in that interval that interpolates the function at these n plus 1 points, then you will be able to find distinct points eta I in the open interval. So, you should be, while showing the result, you should be able to get what these points eta I are. So, you should show the existence of these points eta I, and in addition the result says corresponding to each x in this closed interval a b, there will be a psi depending on x in the open interval a b such that the error in the approximation of the derivative of f by the derivative of the Lagrange interpolation polynomial is given by the expression on the right hand side. The proof runs almost on the same lines as we had done in the case of deriving the error in interpolation, namely this formula. So, let us quickly go through the proof of this result. So, let us now find out what is f of xi minus Pn of xi for I is equal to 0, 1, 2, 3 etc. up to n. So, the theorem says Pn is the Lagrange interpolation polynomial for the function f defined by these points, and so f of xi minus Pn of xi is 0 for I is equal to 0 to n. So, what does that mean? These are the points x0, x1, x2, x3 etc. up to xn, xn minus 1, xn. It says f of x0 minus Pn of x0 is 0, f of x1 minus Pn of x1 is 0. So, this f of x minus Pn of x or f minus Pn evaluated at x0 is 0, at x1 is 0, and therefore, there must be a point between x0 and x1 at which the derivative must be 0. Let us call that point as eta 1. Similarly, it says f of x1 minus p of x1 is 0. So, there must be a point eta 2 belonging to the open interval x1 to x2 at which f dashed eta 2 minus p dashed eta 2 should be 0. So, in general, in the interval xi minus 1 to xi, there will be a point eta I at which f dashed eta I minus Pn dashed of eta I is 0. In each of these intervals, you will be able to find out points eta 1, eta 2, eta 3 etc. eta n such that f dashed of eta I minus Pn dashed of eta I will be 0. So, that immediately shows this result that there exist distinct points eta I in AB. So, you have been able to get those points. What are these points? These are points at which f dashed minus Pn dashed vanishes. So, since this is happening, there exists points eta I for I is equal to 1, 2, 3 up to n such that f dashed of eta I minus Pn dashed of eta I is equal to 0. So, this defines the distinct points eta I, for I is equal to 1 to n. What happens at x is equal to eta I? When x is equal to eta I, f dashed of eta I minus Pn dashed of eta I, just now we showed that it is 0. So, the left hand side is 0. What about the right hand side? At x is equal to eta I, because of the presence of pi n star of x, which is this expression, right, at any eta I is equal to 1 to n, the right hand side is 0. So, there are n points eta I at which the left hand side is 0, the right hand side is 0. So, double star is identically satisfied, it is verified that double star is satisfied. So, let us write down this result. So, now when x is equal to eta I for I belonging to say the set 1, 2, 3 up to n, we observe that both sides of double star are 0. Let x be fixed and x belongs to the closed interval a b. And let us define a function as follows. Say a function chi such that chi of t is equal to f dashed of t minus p n dashed of t minus f dashed of x minus p n dashed of x divided by pi n star of x into pi n star of t. Let us evaluate chi at this eta I. Chi at eta I is f dashed of eta I minus p n dashed of eta I minus this expression f dashed of x minus p n dashed of x by pi n star of x, which is a scalar, into pi n star at eta I. So, this difference is 0 and the second term is 0 because pi n star of eta I is 0 and therefore, this is 0. For what values of I? I is equal to 1, 2, 3 up to n. So, let us find out what is chi at x. So, it is f dashed of x minus p n dashed of x minus f dashed of x. So, here f dashed of x minus p n dashed of x by pi n star of x into pi n star at x. So, I observe that this is f dashed of x minus p n dashed of x minus you have f dashed of x minus p n dashed of x. So, this is again 0. So, you observe that this function chi vanishes at how many points? At all the eta I which are n in number, which are distinct, and at x where x belongs to a b. So, chi of t vanishes at n plus 1 points in the interval a b. Applying Rolle's theorem, we will have the nth derivative of chi vanishes at some point, say psi, at some point psi, and therefore, we compute the nth derivative. The nth derivative of chi will be the n plus 1th derivative at t, because I already have a first derivative here. So, I differentiate it n times. So, I have a n plus 1th derivative at t, then minus, what about this? This is a polynomial of degree at most n minus 1. So, when I take the nth derivative, this will be 0. This is anyway a scalar. So, I have minus f dashed of x minus p dashed of x divided by pi n star of x into the nth derivative of pi n star of t. So, what will be the nth derivative? Pi n star of t will be t minus eta 1, t minus eta 2, etc., t minus eta n. So, it will be of the form t power n plus some coefficient into t power n minus 1 plus etc. So, when you take the nth derivative of the first term t power n, that will give you n factorial. Then the nth derivative of the next terms which appear there, they are all of degree less than n, and therefore, they will not contribute to the nth derivative. So, we get chi nth derivative of chi to be this, and the result that we have got says there is a point psi which depends of course on x, such that the nth derivative vanishes. So, the nth derivative equal to 0 will immediately give us the expression that f dashed of x minus p n dashed of x is equal to n plus 1th derivative evaluated at psi multiplied by pi n star at x divided by n factorial. And you observe that this is essentially the result that we have given in double star, where pi n star of x is the product of n factors of the form x minus eta 1 etc. x minus eta n. So, the theorem tells us that when Pn is the Lagrange interpolation polynomial of degree at most n for the function f, then its derivative Pn dashed approximates the derivative of f, namely f dashed, and the error in such an approximation is given by this expression. There exist points which are distinct eta 1, eta 2 etc. eta n in the open interval a b, such that this happens. That is what the result says. So, this tells us that the derivative of the function f can be reconstructed by the derivative of the Lagrange polynomial that reconstructed the function f at a certain set of distinct points. That is what the information obtained from this result. Let us now go back to the result that we wrote earlier. Starting from the Lagrange interpolation polynomial and the expression for the error in interpolation, we took the derivative and said f dashed of x minus p n dashed of x is this expression. And we also remarked that we cannot get an estimate for this error, because the second term involves the n plus 1th derivative at psi, which depends on x, and we do not have an explicit expression for the dependence of psi on x. However, this result is useful at the nodal points. Let us see what happens at the nodes, namely at the xi, what happens to this formula. So, at xi for I is equal to 0, 1, 2, 3 etc. n, we compute what is f dashed of xi minus p n dashed of xi, and we observe that it is pi n plus 1 dashed of xi into n plus 1th derivative at psi of xi divided by n plus 1 factorial. Then let us look into the second term. The second term involves pi n plus 1 of x. What is pi n plus 1 of x? Pi n plus 1 of x is x minus x naught, x minus x1 etc. up to x minus xn. So, pi n plus 1 evaluated at xi will be xi minus x naught, xi minus x1 and so on. There will be a factor xi minus xi into xi minus xn, and so this is 0. And therefore, at the nodes xi, the second term vanishes, and therefore, we have an estimate of the error in approximation of the derivative f dashed by the derivative of the Lagrange interpolation polynomial as given by the right hand side. So, at the nodes we have an expression by means of which we will be able to obtain an estimate on the approximation that we have made in computing or in estimating what f dashed is. So, let us illustrate this by means of, say, a quadratic interpolation polynomial and obtain what this error is. given the function values say at x naught f of x naught, x1 f of x1, x2 f of x2, p2 of x is the interpolating polynomial, which is the quadratic interpolating polynomial, that interpolates the function at the set of points x0, x1, x2. So, it is the interpolation polynomial for the function f. So, what is P2 of x? P2 of x is, we know, is L0 of x into f of x0 plus L1 of x into f of x1 plus L2 of x into f of x2. That is the interpolation polynomial. What are L0, L1, L2? So, L0 of x will be equal to x minus x1 into x minus x2 into x0 minus x1 into x0 minus x2 multiplied by f at x0. And what about L1 of x? L1 of x will be x minus x0 into x minus x2 divided by x1 minus x0 into x1 minus x2 into f at x1. What about L2 of x? X minus x0 into x minus x1 by x2 minus x0 into x2 minus x1 into f at x2. So, we require now, in order to estimate this, we require P2 dash at each of the xi. So, we write down the expression for P2 dashed. So, P2 dashed will be L0 dashed of x into f naught. I shall use the notation that f of xi is fi. So, f of x naught is f naught plus L1 dashed of x into f1 plus L2 dashed of x into f2. So, we must find this at the nodes x0, x1 and x2 and then use this to get an estimate on the error. So, let us work out the details for L0 of x. So, what is L0 dashed of x? It is going to be, so I have a x square minus x into x1 plus x2 in plus x1 x2. So, when I take the differentiation, then 2x minus x1 plus x2 divided by x0 minus x1 into x0 minus x2 and multiplied by f naught. Similarly, we compute L1 dashed of x. So, that is 2x minus x0 plus x2 by x1 minus x0 into x1 minus x2 and multiplied by f at x1. And here L2 dashed of x will be again 2x minus x0 plus x1 by x2 minus x0 into x2 minus x1 into f at 2. Let us work out the details in a simple case. Suppose the points are equally spaced. The result can be worked out for an arbitrary located points xi also, but in order to simplify our computations, we consider the case that the points x0, x1, x2 are equally spaced. So, which means x1 is x0 plus h and x2 is x0 plus 2h. So, we use that information and find out what is L0 dashed at x. So, it is 2x minus x1 plus x2. So, x1 plus x2 will be equal to 2x naught plus 3h. So, L naught dashed x will be 2x minus 2x naught plus 3h and divided by x naught minus x naught minus x1. So, minus h into x naught minus x2. So, minus 2h. But where do I require L naught dashed? At each of these nodes. So, let us evaluate L naught dashed at x naught, L naught dashed at x1 and L naught dashed at x2. So, x is x naught. So, 2x naught will go. So, I am left with minus 3h by 2h square. So, it is minus 3 by 2h. Let us work out L naught dashed at x1. So, this will be 2x1. So, 2x1 minus 2x naught will give you 2 times h minus 3h. So, this will give you minus h divided by 2h square and therefore, this will give you minus 1 by 2h. All right. At x is equal to x1, I require L naught dashed of x1. So, this is 2x1 minus 2x naught minus 3h. So, it is 2 into x1 minus x naught minus 3h. So, this will be numerator is minus h, the denominator is 2h square and so you will be left with minus 1 by 2h. Fine. So, let us now compute L naught dashed at x2. So, that will give you 2x2 minus 2x naught minus 3h. So, it is 2 into x2 minus x naught which is 2h minus 3h. So, the numerator will be h divided by the denominator is 2h square and so that will give you 1 by 2h. So, we have the results for L naught dashed evaluated at all the nodes. So, this must be done for the other derivatives also. So, let us find out what is L1 dashed at x naught, L1 dashed at x1 and L1 dashed at x2. So, L1 dashed at x naught will be 2x naught minus x naught. So, that will give me x naught then minus x2. So, it is minus 2h divided by x1 minus x naught into x1 minus x2. So, that will give you 2 divided by h. What about L1 dashed at x1 will be 2x1 minus x naught minus x2. So, 2x1 minus 2x1 is 2x naught plus 2h minus x naught minus x naught minus 2h. So, 2x naught cancels, 2h cancels. So, the numerator is 0. So, L1 dashed at x1 is 0. So, let us now compute L2 dash L1 dashed at x2. So, 2x2 minus x naught minus x2. So, that will give you x2 minus x naught which is 2h and the denominator is h into minus h. So, h into minus h and that will give you minus 2 by h. So, the derivatives are also computed at the node points for L1. So, we require L2 dashed at x naught, L2 dashed at x1 and L2 dashed at x2. So, let us see what we have. L2 dashed at x is given here. So, at x naught 2x naught minus x naught minus x1. So, that will give you x naught minus x1 and so that is minus h by what is the denominator? x2 minus x naught, that is 2h, into x2 minus x1, that is h. So, that gives you minus 1 by 2h. What about L2 dashed at x1? That will give you 2x1 minus x naught minus x1. So, it is x1 minus x naught, which is h, by 2h into h. So, it is 1 by 2h. So, what is L2 dashed at x2? 2x2 minus x naught minus x1. So, it is 2x naught plus 2h minus x naught minus x naught minus h. So, that will give you h. So, h divided by 2h into h, and that will give you 1 divided by 2h. So, let us just check what is L2 dashed at x2. 2x2 minus x naught minus x1. So, 2x naught plus 2h minus x naught, x1 is x naught plus h. So, minus x naught minus h, and that gives you h, and therefore, L2 dashed at x2 has been computed. So, we have evaluated all these derivatives at the nodal points. So, we can now write down what is Pn dashed, in this case P2 dashed at the point x naught, P2 dashed at x1 and P2 dashed at x2. So, we have computed P2 dashed as a linear combination of the derivatives. So, P2 dashed at x naught will be L naught dashed at x naught. So, minus 3 by 2h into f naught, then plus L1 dashed at x naught. So, 2 by h into f1, and then plus L2 dashed at x naught. So, minus 1 by 2h into f2. And so, if I write 1 by 2h into minus 3 f naught plus 4 f1 minus f2, then P2 dashed at x1. So, L naught dashed at x1, what is it? It is minus 1 by 2h into f naught plus L1 dashed at x1, that is 0, plus L2 dashed at x1, that is 1 by 2h into f2. So, it is 1 by 2h into minus f naught plus f2. Then P2 dashed at x2 is L naught dashed at x2. So, 1 by 2h into f naught plus L1 dashed at x2 minus 2 by h into f1, then plus L2 dashed at x2. So, plus 1 by 2h into f2. So, this again gives you 1 by 2h into f naught minus 4 f1 plus f2. So, you have evaluated the derivative P2 dashed at the nodes. So, we now have what is f dashed of x naught minus P2 dashed of x naught. So, let us write down the terms on the right hand side and then get the estimate for this difference f dashed minus P2 dashed at the nodes. So, I have to now consider the right hand side. So, the right hand side will be pi n is 2. So, pi 3 dashed at xi into n plus 1th derivative of psi of xi divided by n plus 1 factorial. So, let us evaluate at I is equal to 0, namely at x naught. The right hand side will be pi 3 dashed at x naught into third derivative. So, here again n is 2. So, I can write the third derivative by third derivative. So, here again n is 2. So, 3 factorial. Anyway, for any n the result is available here. So, I substitute n as 2. So, I have to compute this. So, pi 3 dash of x naught into third derivative at psi of x naught divided by 3 factorial. So, we require pi 3 dashed of x, and then we shall evaluate at the nodes. What is pi 3 of x? Pi 3 of x is x minus x naught into x minus x 1 into x minus x 2. Since we work out the details for equally spaced points, so we can substitute the details. So, x minus x naught into x minus x naught minus h into x minus x naught minus 2h. So, everything is in terms of x naught and h. So, we require the derivative pi 3 dashed of x. So, that will be x minus x naught minus h into x minus x naught minus 2h into derivative of x minus x naught, which is 1, plus x minus x naught into x minus x naught minus h into derivative of this, and thirdly x minus x naught into x minus x naught minus 2h into derivative of this term, which is again 1. So, we evaluate this at x naught. So, when x is x naught, you get minus h into minus 2h. From here, when x is x naught, this is 0, x is x naught, this is 0. So, it is simply 2h square. And then let us find pi 3 dashed at x naught x 1. What is it? It is pi 3 dashed at x naught plus h. So, I substitute x as x naught plus h, this goes, and then I substitute x as x naught plus h, this term also goes. So, from here x naught plus h minus x naught, so h, and x naught plus h minus x naught minus 2h, so minus h. So, this will give me minus h square. And then let us work out pi 3 dashed at x 2, which is pi 3 dashed at x naught plus 2h. So, we observe that at x naught plus 2h this factor vanishes, x naught plus 2h this also vanishes. So, I have x naught plus 2h minus x naught, so 2h, x naught plus 2h minus x naught, what is that? This is x naught plus 2h minus x naught. So, they will get 2h minus h, so which is h, and so it is 2h square. So, the right hand side, in the right hand side we have this term and we have evaluated that term at the 3 nodes x naught, x 1, x 2. So, we shall now substitute. What is pi 3 dashed of x naught? It is 2h square by 3 factorial into the third derivative at evaluated at psi of x naught. So, it is simply h square by 3 into the third derivative psi of x naught. Then at x 1, the right hand side is going to be pi 3 dashed at x 1. So, minus h square by 3 factorial into the third derivative psi of x 1. And then at x 2, we have the right hand side to be given by 2h square by factorial 3 into third derivative psi of x 2. So, we have the expression for the right hand side. We computed the derivatives of P2 at the nodes. So, we can now write down this estimate at all the nodes. So, at x naught, what do we get? F dashed at x naught minus P n dashed of x naught is the right hand side, which is h square by 3 into the third derivative of f. So, this tells you f dash of x naught, the derivative of f at the node x naught can be approximated by, here I have approximated by a quadratic polynomial. So, I shall write this as p2 dashed. So, p2 dashed of x naught plus h square by 3 into the third derivative psi of x naught, and we have obtained an expression for p2 dashed at x naught, I mean that is 1 by 2 h. So, 1 by 2 h into minus 3 f naught plus 4 f1 plus f2, 4 f1 minus f2. So, minus f2, and error in this approximation is h square by 3 into third derivative evaluated at psi of x naught. So, that is the approximation for f dashed of x naught. So, now I can write down the approximation for f dashed at x1. So, it is p2 dashed, which is 1 by 2 h into minus f naught plus f2, and the error has been computed here, which is minus h square by factorial 3 into the third derivative psi of x1, and finally the estimate for f dashed at x2 is going to be 1 by 2 h into f naught minus 4 f1 plus f2, and error in this approximation is 2 h square by factorial 3. So, I can simplify and write h square by 3 into the third derivative at psi of x2. So, we used this expression which was obtained from the expression for error in interpolation by differentiating it and evaluating that at the nodes xi, I is equal to 0 to n, and we illustrated this for the case of a quadratic interpolating polynomial that interpolates the function f at the set of 3 points x naught, f naught, x1, f1, x2, f2, and we now have approximations or estimates of the derivative at the nodal points.